Welcome to the Chemical Physics Laboratory at Concordia University in Irvine, California. This laboratory that we're sitting in right now was built up from donations from a variety of private individuals, universities, and corporations and foundations here in Southern California and all across the United States. It's amazing that this laboratory is here in the form that it is today. The instruments that you see here are all operated, maintained, calibrated, repaired, and modified by undergraduate science majors here at Concordia. On this table, this is a combination of instruments to do light emission or luminescence spectroscopy. A fast CCD instrument right here, and a high precision scanning luminescence instrument right here. A variety of lasers, arc lamps, choppers, and optical elements allow us to design just about any type of experiment you want. In this laboratory, what we try to do is measure the absorption, emission, and scattering of light. And so all the instruments, all the optics, all the electronics, all the computers are dedicated toward this goal. All of the instruments are customized, in other words, taken beyond where they were at the factory and modified to do the special experiments that we have in mind. Over here we see some of the detection electronics for detecting and analyzing the light that we get out, operating the lasers. And now moving over to our next table, this is our Raman instrument, our argon ion laser, air-cooled, and the Raman optics and the Raman instrument measuring inelastic light scattering. As we go to the next table, I want to draw your attention to all the tools in the laboratory. Since we design, build, and modify our own instruments, our undergraduate students have to know how to work with tools to work on the instruments. So this is a very active area where all these tools are used on a regular basis. So on this table we have two light absorption instruments, a diode array UV visible spectrophotometer for very quick work, and a high precision scanning UV visible spectrophotometer made by Online Instrument Systems as a modification of the classic Carry 14 instrument. And then we have on this table an infrared spectrophotometer and a general emission excitation luminescence spectrophotometer that we're in the process of modifying. Let me draw your attention to a couple of the posters here in the laboratory. These were poster presentations on research done by Concordia undergraduates in this laboratory and presented at regional or national meetings of the American Chemical Society. The names are important in that the students on these posters have gone on. They have graduated from Concordia, and in the case of this green poster over here, all of the students working with me are either in medical school or physician assistant school. And on this poster we have now students who have graduated, who are getting doctoral degrees in chemistry, working in medical research, going on to dental school and physician assistant school. So the research not only creates new results, but creates outstanding scientists and scientific professionals who go on to do important work in the scientific. We're standing here at a tree knee-type vertical milling machine at the Chemical Physics Laboratory at Concordia University. This tool, donated to us from Harvey-Mudd College and repaired and calibrated by Concordia undergraduate science students, is an example of the kind of tooling we use to design new equipment for our scientific research initiatives or to repair or to modify equipment. The milling machine allows us to cut planes and angles. So anything that is rectangular or angular needs slots or grooves or holes in it, the milling machine can do for us. I want to cut now over to our Rockwell lathe, donated from University of California, Riverside, and also lovingly restored by Concordia undergraduate science students. This milling machine, this lathe, with digital readout, is used to cut parts that are cylindrical or circular to drill, to tap, to do a variety of functions in the laboratory. And again, between the lathe and the milling machine, we have the capability to make virtually any type of part we need for the laboratory. And finally, we have a drill press for general drilling work as well. These three tools comprise, at the present time, the major machine shop tools that we have here in the Chemical Physics Laboratory at Concordia University. They are used to support the laboratory and for our undergraduate teaching in the sciences at Concordia. The Chemical Physics Laboratory is named in honor of Glenn A. Crosby, a world-class spectroscopist and physical inorganic chemist who, upon his retirement from the chemical physics program at Washington State University, donated his entire laboratory, including most of the equipment that you see here, to Concordia University to establish the Chemical Physics Laboratory. He did this because he believes in the importance of undergraduate research in the small Christian liberal arts university setting, and he is concerned and strongly committed to promoting excellence in science for future generations. Added to this collection are a number of equipment donations from other scientists and other universities who share with Dr. Crosby a passion for the importance of undergraduate involvement in scientific research and educational programs that use first-class scientific equipment, such as what you see here in the laboratory. Welcome to the advanced synthesis area of the Chemical Physics Laboratory, where we build and purify we make and purify molecules and solvents here. What you're seeing right now is a high vacuum inert gas line, oil diffusion pump, low temperature trap, and two valved glass lines that allow us to pump all the air out and to put a non-reactive inert gas such as nitrogen or argon in. This line allows us to do chemistry that could never be done on the lab bench. In other words, to make, to purify, to transfer, to manipulate molecules that are so reactive that they might fall apart if we tried to do this open to the air on the laboratory bench. Here's another gas purification unit right here, and here is a liquid chromatograph to separate and purify samples that might have a number of molecules and impurities in them. We can use this instrument to purify them. And now another air-sensitive line with vacuum and inert gas, and some of the specialty glassware we use to do chemistry in the absence of air. Air, as we breathe it, has three chemicals that may interfere with our reactions. There is atmospheric water, moisture in the air. There is oxygen in the air, very reactive molecule. It reacts with us, and that's how we breathe. And there's also carbon dioxide in the air, which can cause problems. With apparatus such as this, with technology such as what we have here, we can do chemistry in harsh and hostile conditions. We can hold and manipulate and analyze molecules that we can never get under earthly terrestrial conditions. So this is a very important part of our effort, and it's a companion laboratory to the spectroscopy laboratory downstairs. In the Chemical Physics Laboratory, not only do we have to build a new apparatus for spectroscopy, but we often have to build and design or repair glass apparatus that we use upstairs in the synthesis laboratory. What I'm doing right now is a very simple but very important type of glass work. I'm heating this glass tube in a glass torch flame, and what I'm planning to do is to heat the glass up and bend it to prepare it for use in the laboratory. So here we go. The very bright yellow color is due to sodium in the glass, and we're getting it hot enough so that it can bend, and there we go. We're going to bend that tube, and in just a minute it'll solidify, and we took that straight tube and we gave it a 90-degree bend. A very simple glass operation, but nevertheless extremely important that we know how to do this basic class manipulation. It turns out that many of the samples that we measure spectroscopically here at the Chemical Physics Laboratory emit light in particular. So they luminesce or glow or emit light. They emit light best at very low temperatures. And so here I have a thermos bottle with an inside and an outside wall, and evacuated. All the air is pumped out in between the two walls. In this thermos bottle I can place liquid air or liquid nitrogen, minus 196 Celsius, way colder than dry ice. And I'm going to do this right now. So I'm going to put a little liquid nitrogen in this thermos bottle and show you how we measure at very low temperatures. So what you see spouting out here is condensed water vapor from the air, and down below we're starting to get a fill with liquid nitrogen. So here it's coming on up. Notice I have eye protection, hand protection, and body protection in the form of gloves, a lab coat, and safety glasses to protect me from the extreme cold. So now that we've filled this with liquid nitrogen, we have some bubbles coming out. Our next step to get our sample very cold would be to put the sample, which in this case is in the form of a liquid, dissolved in a liquid in a very narrow, long test tube, which, by the way, we made ourselves using glass techniques. And we'll set that right inside the double-walled windows of this thermos bottle and cool it down to the temperature of liquid nitrogen, and then we can bring laser beams in and look at the light being emitted. Now, you might ask, why are we doing all this? Why all this equipment here in the laboratory for spectroscopy? Why the lathes and the milling machines? Why the glass blowing? Why all the air-sensitive chemistry? What are we trying to do? Well, it turns out that the outermost electrons, the valence electrons, or the outermost electrons of molecules and of atoms, are those involved in chemical bonding, in defining chemical structure, and in defining the way molecules react one with another. So chemical reactions, structure, and bonding are governed by these outermost electrons. We're using light to probe, to figure out, to touch those outermost electrons, to figure out what they're doing, where they're going, and how they're interacting in a particular molecule. So all that we do, we're making molecules to have certain bonding, structural, and chemical relationships, and we're probing the electrons to figure out how they're working so we can understand at a molecular level and at an atomic level what's happening. Knowing that, we can then design molecules with specific properties, perhaps to cure cancer or to absorb light from the sun and turn it into electricity. It all starts, though, with knowing what those electrons are doing, being able to design molecules that behave in certain ways, and verify that behavior spectroscopically. And in the meantime, creating a wonderful generation, excited, well-prepared, enthusiastic of new scientists. So there we have it. Up until this point, we have talked about the Chemical Physics Laboratory in terms of atoms and molecules that we produce right here in the laboratory or in the laboratory upstairs. But we can also look at molecules and atoms millions of miles away, as far away as the moon or the sun, or if you wish, using a telescope, collecting light from distant galaxies or stars in our own Milky Way galaxy. I have an example here of what I mean, and we'll go over what it is and how we acquired it. On this computer screen, we see a portion of the solar spectrum, the spectrum of the sun, recorded here in the Chemical Physics Laboratory. And I want to draw your attention to these two closely spaced dips with a little bump in between. What we have with one of our medium resolution spectrophotometers is the famous yellow sodium doublet, double line emission of the element sodium seen in the sun. And in between the two lines is a little bump, and this is due to an emission from nickel, the element nickel in the sun. This again acquired here in the Chemical Physics Laboratory on our medium resolution spectrophotometer. Let me show you how we did it. In my hand, I'm holding loops of a small fiber optic cable. The output of the fiber optic cable is, in this case, directed to the input light collection optics for our Raman instrument. This is our highest resolution instrument. And the light from the sun goes into the entrance slit, goes through the dispersing elements in the instrument, back out to the photomultiplier tube, and then digitized as a function of wave number or wavelength to get the spectrum that you saw. Actually, this particular instrument will give an even higher resolution spectrum, considerably higher resolution than the one I showed you. But the idea of taking a fiber optic cable, one end goes out to harvest sunlight, the other end of the fiber optic cable emits light into our light collection optics. This general idea shows you how to do astronomical spectroscopy. All we have to do, if we're looking at a distant faint light source, let's say a weak star emission, is to align the fiber optic cable in the output eyepiece of a telescope, in the focal plane of the telescope, pick up light that has been collected by the telescope, and then direct it through our spectroscopic instrument. And we have this capability here in the Chemical Physics Laboratory as we partner with Tierra Astronomical Institute with their telescope systems.